Hello, in this video I'm going to say a little bit about Rene Descartes. We've mentioned Cartesian coordinates quite a few times already, so it's useful to know a little about the man who gave rise to them. So here's a famous portrait of him rocking King Charles Spaniel look. He was operational in the first half of the 17th century, so he was born at the end of the 16th century, and then he was active throughout the first part of that next century. And he covered a lot of different areas. So let's have a look at what those areas were. So he was a French philosopher, scientist, mathematician, as was often the way back then. People covered a lot of different things. They were much more in their beginner state, so pioneers in different topics. They could work in a number of different fields because they were all so closely related, and there was a lot of ground to be covered relatively quickly. That's not to say it was all easy back then, because they were starting from a different starting point, so it was still very difficult, but they could cover a lot more areas, and Descartes was no exception. I mean, he was prolific in a lot of different areas, particularly those three, and he completely revolutionized mathematics, and this had a big knock-on influence in Newton, who of course was active in the second half of the 17th century. And it influenced a lot of other people as well. But, we're talking a lot about Newton at the moment, going through classical mechanics, or we certainly will do if you haven't reached those videos yet. So I suppose the main thing you could probably sum up was he brought a lot more algebra into mathematics and science through his system of Cartesian coordinates. So how did this happen? Well, this is analytic geometry. This is the big area. This is really geometry using Cartesian coordinates rather than the Euclidean style of geometry and approach that we looked at on the video on Euclid. So if you remember, with Euclid, we were talking about constructing shapes using a compass and a straight edge, and there was nothing algebraic about it. It was all very real world. How can we construct a particular shape? How can we calculate what the area might be? Things like that. It wasn't to do with, well, here's some unknowns. Here's how we go about solving a problem, which we might use a square or a triangle in or something like that. It's much more describing things in the real world and keeping things then to 3 dimensions at most. So talking about lines, then plane shapes in area, and then solids in volume. Now, Descartes, with his coordinate system, meant a lot of these things could change. So if we were going to be operating in 2 dimensions, say, then we've got our set of Cartesian axes, which are our xy coordinates that we're going to have. So say we had a square that we were going to put into this pair of axes, into this Cartesian space, this 2-dimensional Cartesian space. Now we can specify corners according to their coordinates. Say, we might say, well, that's at 1 and 3, that's at 1 and 3. So here we are, we've got coordinates there for all of these different things. We're specifying exact points in space. You can then talk about lengths of lines as distances between points in space. We can talk about areas off of that. We can write down equations for various lines. We can say this is the line y equals 3 here. We can have a line for the diagonal and start saying that's our line y equals x between certain values. For x is between 1 and 3 inclusive. So we're adding a lot more of these things in, and then we can start solving problems. We can start saying, well, what if we don't know a certain thing? What if we've got a square constructed off of this diagonal? What would it look like? Where would the corners be? Writing this stuff out algebraically in a way that we just can't do with the Euclidean approach. So this can then feed into all manner of things, because if you're then someone like Newton, who might be, or Kepler or someone like that, looking at data of observations of planets going around the sun, or you're look, you're Galileo and you're looking at these, the motion of objects. I know Galileo was before Descartes, but if you were having that sort of data and you wanted to then turn this into mathematical statements that you can then solve, because he's chucking these cannonballs supposedly off the Leaning Tower of Pisa, well, we can start quantifying these things. We can start writing these mathematical expressions. We can start solving things algebraically. If we didn't have this sort of algebra involved, then it's hard to imagine Newton and Leibniz and such like coming up with calculus so soon after all of this. Excuse me. So it really was revolutionary, and we still use this stuff today. This is what we do in our school learning of mathematics, and for good reason. It's immensely powerful. It does have the downsides that we seem to have lost sight of a lot of the Euclidean approach and that real world type of geometry. And maybe we've become too abstracted in a lot of our learning, that we've gone too quickly to the algebraic side. But that is because it's so powerful. We can then use this approach. We use this in vectors. We use it in so many different things. So yeah, it really was, massively, massively important. Now, this isn't all that Descartes did, of course. I mean, he was a very famous philosopher. His ideas are still studied in philosophy again today. I mean, it still comes up. There's two main ideas, I suppose, that he's associated with nowadays. So you've got the cogito statement for Cartesian doubt, this cogito ergo sum, which is most commonly translated into I think, therefore I am. Quite often misused nowadays, I would say. The idea behind this was this problem of Cartesian doubt. What can we believe? How do we know we're not in the Matrix, to put it into modern terminology? How do we know we haven't got some evil demon that's probing our senses and actually the real world is just fantasy? It's not there. It is just being created, and we're experiencing this false reality. So how do we know that that isn't the case? I mean, this leads towards this extreme skepticism of doubting everything. How do we know any of this stuff is here? How do we know that this pen that I'm holding and this laptop that I'm writing on, how do I know they exist? I mean, this is a real problem. So Cartesian stripped it all the way back. He just kept on cutting back, trying to find, well, what can I be certain of? And it was, his doubts, the fact that he was doubting the existence of these things, proved that he must exist in some way in order to have those doubts. So the fact that he was thinking means that he must exist. So his existence is proved by the fact that he's thinking. I think, therefore I am. So it's not the how could I put it? It's not the way that sometimes people misuse it nowadays, where they're saying, thinking is what gives meaning to my life. It's not a statement of meaning. It's a statement of existence. It's a statement of some kind of certainty in the world when you're gripped with extreme skepticism. So that's what's going on there. Another part of Cartesian thought, which is still, I suppose, still well known, it still comes up in beginner philosophy courses, is this Cartesian dualism, this mind-body dualism. And this was influenced by, science has just started coming to the fore in the, say, late 15th and then the 16th centuries. And then you've got Descartes riding in on this early wave, where you've got these scientists describing the world in very mechanistic ways. I mean, you think of how Newtonian classical mechanics is put together. It's very, this causes this. We've got some equations that describe this behavior. It's very mechanical. So we can take an event and we can then describe the causes. And this is how people started describing the body, in this mechanical fashion, which, not surprisingly, left them with this, not sure if this is really cutting the mustard. We don't feel like machines. Science seems to be describing things in this machine-like fashion, but we as people don't seem to be behaving like machines. I mean, surely we have our we have will that we can exert on the world, and we can make things happen. We're not just simple machines. So he came up with this dualism between the two of them, that you've got this mechanical body and this non-mechanical mind, where we have free will in order to make things happen. The body is physical, the mind is non-physical, and these two things are somehow connected to each other in that the mind can control the body, but they're separate in both their nature and how they're made, how they behave, how they're constructed. So that's the Cartesian dualism that was very influential and popular for quite a while. Of course, nowadays things have moved on considerably. I suppose if you think more recently in terms of philosophy of mind, the sadly recently departed Daniel Dennett, the great American philosopher, who pretty much spent his entire philosophical career fighting against variations on Cartesian dualism. We don't have this thing which is lurking around inside us. There is no separate experiencing of the world which is separate from us actually taking in information with our senses and perceiving it. That is the totality of our experience in the world. There isn't some kind of screen where we're sitting there observing our sense data and then interpreting it in some fashion. There's no separation here between the mind and body in that way. It's one unit, and we experience it in one totality. That doesn't mean to say that we know how to explain it all. There are certainly questions as to where it all comes from and how it manifests itself. But that separation is something that a lot of philosophers certainly argue against nowadays. But it was hugely influential back in the day. So it's another one of those ones where it's you need to know what you're arguing against, really, don't you, if you're going to be taking a new position. So if you do get into philosophy, these will be two of the ideas that you'll be looking at fairly closely. So yeah, but in terms of what we're looking at here, it's the analytic geometry that is the most important part of Descartes' thinking, and this abstracting, moving into more problem-solving space for working out solutions to things. So yeah, really massively influential figure in the history of the world, really.